Hello, welcome to my talk all about the fluids. This talk is on the turbulence modeling, basic equations, part 2, turbulent transport equation. In this talk, the detailed derivations of the turbulent transport equations are presented, including the transport equation for the Reynolds stress component, turbulent kinetic energy, and the dissipation rate. In addition, the Boussinesq assumption is presented with a short discussion with the assumption. I must admit that in this talk, there are a lot of mathematics and the relevant equations. I will try to present this equation in a more understandable way, and to make the equation correct, I derived all the equations myself and then checked and double-checked all the equations against some well-known books and published papers, and thus hope all this would be useful for you. In this slide, a Navier-Stokes operator is defined based on the conventional Navier-Stokes equation. We considered the incompressible flows here. This Navier-Stokes operator is of vital importance in the derivations of the turbulent transport equation. As we have seen in many textbooks, the Navier-Stokes operator, the fancy capital L, is defined as this. Basically, this moves the terms of the right-hand side together with the left-hand side term. Here, ui is the velocity component I. For the Navier-Stokes equation, this can be understandable, since this is the moment equation for the velocity component ui. However, when we defined the Navier-Stokes operator, it is an operator with ui as the main variable, but it is also with some other components, here fi and xi. Thus, the author believes a better expression for the Navier-Stokes operator should be given as this. Here, q is the generalized variable of the component I, and it can be either ui, fi, or xi. And in this talk, I will use this expression, but I must say here, for this expression, it would lead the exactly same result as those in the traditional Navier-Stokes operator, but I think this is with a better physics. As such, for the component j, we have the ns operator as this. So based on the Navier-Stokes equation, we could have both the equations for LQi and LQj are 0. Thus, we can construct an equation as this and take the average of the equation. We have the equation we can use to derive the transport equation for Reynolds stress component. Now we can substitute the Navier-Stokes operator into this expression. We have this, and we can exchange the order of the averaging operation and the pluses or minuses. So we have the expression as this for the first part of the expression and the second part of the expression. And then we can put all these corresponding terms together. The first term together into this, and the second term this, so we have this. The third term for the body force, we have the expression as this. The fourth term with the pressure gradient, so we have this. And the last term with the fluid with cost term, we have this. And we can turn these terms into 1 to 5. And in the next few slides, we will do more mathematical derivation for each of these terms. For the first term, we can separate the expression by timing the relevant terms together as this. Now, since the averaged velocity kept ui and uj would be constants regarding the averaging operation, thus they can be taken out of the averaging operation. So we have this. Put these two terms together, we have this term. Obviously, the averaging on the single fluctuating velocities u prime I and u prime j would be 0. Therefore, the final expression for the first term is given as this. The second term has an expression as this. Now we time the relevant terms together, so we have the expression as this. Now we can take the mean velocity, capital UI, capital UK, capital UJ, out of the averaging operation. We have the expression as this. In here, the continuity equation for the mean velocity, capital U, and for the fluctuating velocity, U prime, are also used. Look at the expression. So the first two terms would be 0. Therefore, we have the expression as this. We also put this and this together. We have the term as this. So the final expression for the second term is given as this. For the third term, the body force would be generally given and specified. Thus, it is not relevant to the fluid turbulence. For instance, the gravitational force of the fluid is one of the body force, which is proportional to the fluid volume or mass. Therefore, it is independent of the fluid velocity. As such, we can take the body force out of the averaging operation. So we have the expression as this. Look at the averaging of the single fluctuating velocity. So we have the expression for the third term as 0. The first term is for the pressure gradient. Timing the relevant terms together and also take out of the averaged pressure out of the averaging operation, the capital P here and here. So from this expression, we can see these two terms would be 0. Hence, we have the expression as this. Now we can do more mathematical manipulation for this expression, we have the final expression for the fourth term as this. For the fifth term, this is relevant to the fluid viscosity. We can separate all these terms, so we have the expression as this, and we can take the mean velocity out of the averaging operation. We have the expression as this and this. Here again, the averaging of the single fluctuating velocity u prime j and u prime I would be 0. Thus, we have the expression as this. And we can do a little bit more derivation for this term. We have this. Since we can see this term came to here and this came to here, so we have the expression as this. And put these two terms together, we have the expression as this. So the final expression for the fifth term is given as this. In this slide, we put all these 5 terms together, so we have the transport equation for the Reynolds component. So the equation given as this complicated equation. And we can write this into a conventional transport equation for the Reynolds component. We have this, and the two terms on the left-hand side are this, and all other terms we put on the right-hand side. So if we use the Reynolds tensor, tau ij equals to minus average of the fluctuating velocity u prime I and u prime j. And then we can write the transport equation for Reynolds tensor as this. The transport equation for the Reynolds tensor is an equation we derived for solving the Reynolds tensor. For the Reynolds tensor, it is a symmetric tensor, thus it has 6 unknowns in the Reynolds tensor. As we have shown in the previous slides, the transport equation for Reynolds tensor component would be given as this. Here, the pressure strain term kept pi ij given by this. So for this term, we have 6 new unknowns. And for the diffusion term, Cijk, we introduced 10 unknowns. And for the dissipation term, epsilon ij, we introduce 6 unknowns. So therefore, to solve the Reynolds component, we formulated the transport equation, but we have also introduced 22 new unknowns. And unfortunately, we have no more physical laws for building more equations for these unknowns. More details can be found in the Navier-Stokes book, Turbulence Modeling for CFD. For the turbulent flow, we can define the turbulent kinetic energy K as this, and its relation with the Reynolds tensor component tau ii as this. Therefore, if we set the indices I equaling to j in the transport equation for the Reynolds component, We can obtain the transport equation for the kinetic energy K as this. To solve the energy transport equation above, as we see in the conventional 1 and 2 equation turbulence models, we must model some terms on the right-hand side of the equation here. So the dissipation rate must be solved with the additional equation in the 2 equation turbulence models. And we'll see the details in the next slides in this talk. Tau ij must be linked with the turbulent kinetic energy, as well as with the mean flow. For instance, using the Boussinesq's eddy viscous assumption given as this. And the term in the red ellipse must be approximated, and the most used approximation in the turbulence modeling is the simple expression given as this. So put this together, the transport equation for the kinetic energy K in the standard K epsilon model is given as this. To understand the transport equation, we can write the equation in this form, following the reference by Derivation, the online book, Fluid Mechanics, Turbulence Flows, and Turbulence Modeling. We generally have 4 different regions in the transport equation for the turbulent kinetic energy, termed using norm number 1 to 4. And this transport equation corresponds to the energy cascade process as assumed by cosmograph as shown in this figure. In the region 1, it can be derived from the Reynolds transport theorem for the quality of the kinetic energy, including the local change of the turbulence energy and the convection of the turbulent energy. The region 2 is the production term, meaning the product of the Reynolds stress tensor and the velocity gradient. In this region, the large energy carrying eddies interact with the mean flow and extract energy from the mean flow and transfer the energy to the eddies of slightly smaller scale. Region 3 is the diffusion term. This region represents the mid-range and isotropic turbulence. The energy transport or diffusion in this cascade process, energy flows from the large eddies to smaller eddies. Here, an unusual fact is the inclusion of the viscous term in this diffusion term. The main reason for this combination might be that the other 2 terms can be simply approximated as the eddy viscous term, as we see in the turbulence models, the item 3 in the previous slide. Region 4 is the dissipation term, epsilon. This term is responsible for the transformation of kinetic energy from the small eddies to thermal energy. And this term itself is positive, meaning the kinetic energy is transferred to the internal energy. Thus, the turbulent energy is dissipated into heat. Now, in this slide, we can use the Navier-Stokes operator to construct an equation for the dissipation rate epsilon, defined as this. So the constructed equation is given as this. Here, LQI is the Navier-Stokes operator for the component QI. So substitute the NS operator into the constructed equation. We have the expression as this. Here we have 5 terms on the right-hand side of the expression, and we will examine all these terms in details in the next 2 slides. For the term 1, we can simply time the terms out and take the average velocity out of the averaging operation. So we have the expression as this. And drop the term with the averaging of the single fluctuating velocity. We have this. And finally, we have the expression as this for the first term. Here, epsilon is defined as this. The second term is much more complicated. We can time the relevant terms together, and we take the terms of the average double velocity out of the operation. So we have the expression as this. This term can be dropped because of the averaging of the single fluctuating velocity. So using the continuity equation for the mean flow velocity capital U and the fluctuating velocity U prime, these two equations, and we can obtain the expression as this. So further, using the rule of calculus for each term in this expression, we get 2 terms in this expression. So using the expression epsilon ij, we have the expression as this. And further, we can write the expression as this. Here, actually, it's the epsilon. So we have the final expression for the second term as this. For the third term, the body force is independent of the turbulence of the flow. Thus, the body force can be taken out of the averaging operation. Therefore, the third term is 0. The first term can be termed out for this averaged and the fluctuating pressure. So we have the expression as this here. The averaged pressure is constant with regard to the averaging operation. So from this expression, we can see the first term here would be 0. Therefore, we have the expression for the first term as this. And we can exchange the order of the derivation here with regard to xi and with regard to xj. If we look at this expression, we can see when we change the order of the derivation, and we have this, and this term would be 0. Therefore, we have the final expression for the first term as this. For the fifth term, in a similar way, we can separate the mean velocity and the fluctuating velocity, and take the mean velocity out of the averaging operation. We have the expression as this. And drop the first term, we have the expression as this. In here, we change the order of the derivations with regard to xk and xj, and further exchange the order inside of the square bracket. We have the expression as this. So if we consider an expression as this, so we can separate this term into 2 terms as this. And the expression for the fifth term would be this. And use the definition for the epsilon, we have the expression as this for the fifth term. Here we put all these terms together. We have the transport equation for the dissipation rate epsilon. And this can be rewritten as in this form. We put these 2 terms on the left-hand side, and all other terms on the right-hand side. This is the transport equation for the dissipation rate epsilon, and epsilon and epsilon ij are defined in these two equations. Based on the book of Wilcox turbulence modeling for CFD, we normally have an isotropic relation for the epsilon ij and epsilon. This is a very simple relation, and it is generally accepted because of the fact of the dissipations happen at the small length scale, for which the turbulent flow would be more isotropic. And then anisotropic expression is given by this, with the correction term here. Fs is the no Reynolds number factor, and Bij is the Reynolds stress anisotropy tensor. There is a difficult problem for solving the transport equation for the dissipation rate. We must model all these terms in this big ellipse. In this slide, a presentation and a discussion would be presented for the Boussinesq assumption. Based on Schmidt, in 1877, Boussinesq reasoned that the Navier-Stokes equation would be still valid for the mean flow in the turbulent flow, but the fluid viscosity is significantly increased due to the fluid turbulence. Thus, he obtained the stresses of the flow given by this Tij, meaning the fluid velocity gradient of the mean velocity. Here, nu b is the imaginary fluid viscosity, and it is equivalent to 2 days total viscosity. Nu b equals nu plus nu t, the fluid viscosity plus turbulent eddy viscosity, as we see in the turbulence modeling. And Boussinesq obtained the relation K equals 1.5 pressure. It should be noted, Boussinesq actually made this assumption 18 years earlier than Reynolds, who proposed the Reynolds stress tensor in 1895. In today's turbulence modeling, for instance, the most applied two-equation turbulence model, it is always assumed that the Boussinesq's hypothesis is linked to the Reynolds stress tensor with an expression as this. Here, tau ij is the Reynolds stress tensor, nu t is the turbulent eddy viscosity, capital Ui and capital Uj are the mean velocities, and K here is the turbulent kinetic energy. If we set the indices I equaling to j, so we have the expression as this, and for the incompressible flows, these two terms would be 0. Therefore, we have the expression as this. We can see tau ii would equal to minus 2k, and here the k is the turbulent energy given by this.